So we stopped at this location where what we did was we derived a function for the stiffness. So we derived an expression for the stiffness of a bar element, right? And we simply going through an example like this to illustrate the applicability of that, right? So you have a tapered bar of uniform thickness of T shown as below. Find the displacement at the nodes by forming into two element model, right? We have to form two elements in this, right? Either you can represent this. Now this A is a function of X. So that means there will be some X term here. And when you integrate it, there will be a different answer for that element, right? So but even you can go with these assumptions, but you need to have a uniform section, right? So that means if you are going to divide this into two elements, you need to have two uniform elements, right? So let's see. So the displacement and the nodes forming into two models, the bar has a density of 88 and Young's modulus of this, and in addition to self weight, it is subject to a point load at P at its center. So determine the reactions as well. So this is a 1D case, right? So you only know one reaction will be there if you know the density and weight, and just 1 kilonewton, you can straight away know the reaction. That's simple, right? You no need to use finite element, but I'm showing you how these methods are applicable, because when the things are getting complex, you can't use manual methods, right? And I will write it here. So first thing is, your element is like this, right? Okay. So I'm dividing it to 2, right? So this thickness is actually, it is like this. This thickness is 10 millimeters. I'll take this as this is how much? So you have this is 80 centimeters. This is so millimeters, I think, right? Millimeters, and this is 40 millimeters. Okay, so and the height of this is 300 millimeters. So you know at the half it will be 150, okay? Right? So in order to use that, people found it more difficult how to use this, right? So you have a stiffness matrix for a uniformly cross-section bar element. So that means you have to find a uniform bar in these two elements, right? So you have some element in this case, you have some area which is larger than this, and the average area will be here, right? So within this region, the average area will look like this, right? So in this portion, it is more than the average, it is less than the average. So you can determine an element like this from the average area. You can determine an element like this, the average area. So now you are able to use the So this is your bar now, right? You have fold it to a different section. The section of this is you have to determine. So how to do is, this length is 80 and the area is 80 into 10. Why? The thickness is 10, right? That's uniform. This is 400 into, sorry, 40 into 10. So that means in the middle point, it should be 60 into 10. Right? And that's average of 80 and 60 is, so this is 70. So I'll multiply it and write the area is 700. It's 800 and 600. The average area is 700. It's 600 and 400. The average area is 500. How to take it is 600 plus 400 divided by 2. Right? So this is our new 2-element bar model, right? So there are 2 elements. So you have 2 stiffness matrix and you have to assemble that. So for each element, you can write a stiffness matrix like this. And you have to assemble it for the global structure. And let me write that. For this case, it's 700, right? So you can write the stiffness matrix. A is AE over L. Let's call this K1. Okay, K1. Okay, so K of the element 1, right? It's written here, K1. One minus 1. So if you substitute, what will be your values? I think L is same, so A is different, right? Because when you assembling it, you need to have same constant here. So for the second element, you can write K2. So this is A1. E is same, L is same. Because why? The lengths are same, 150 and 150. Doesn't matter if you substitute or not. So this is A2 E over L. So A1 is 700, right? A1 is 700 and you can substitute 700 into 2 to the power 5. I don't remember, it is 2 to the power 5. Yes, yes. Into 150. Right? So, and it's 114. And this is becoming 500. to the power 5 to 150, right? So what is common is you can write you can keep this as L, right? And you can write like this. So you can cancel this term with this, right? So you can write this as 10 to the power 6 and okay. So there will be the matrix as well. So you need to keep the same thing as the constant here, right? So you need to bring this term. It would be better if you bring this term or bring this term only to into the matrix, right? So I will be transferring these two. So this is 10 and this is 14, right? So remaining would be 10 to the power 6. So this 0 is there. 10 to the power 6 over 15, right? So the first element would be 10 to the power 6 over 15. So you keep the 14 into the equation, sorry, matrix. So minus 14. Everything will be multiplied by that 14, right? You know the matrix algebra. Okay, so K2 is 10. You keep you push the 10 inside to the matrix. Okay, now understand the concept. So we had a bar element, but the problem is we can't take it as a full element. They ask to separate it as two element, right? And for each element that should represent a bar. But what we had is the stiffness coefficient for a uniform bar, right? So you have to convert it to a uniform bar, right? So we take the average of each portion and take it as the average area, and we define the stiffness matrix. For this is these are for the each element. So in this element you have, this is the first node, this is the second node, this is the third node, right? Okay, so you will have at the first node, so theoretically you should have u1 and a reaction of, let's say, so a force of F1, right? And at here you should have a displacement of u2 and force of F2. Here you will have displacement of u3 at this point. Okay, I can't write this point, that's why I'm writing it outside. And F3 force and the displacement, right? So this tells you, this is the simplest form, right? This tells you how the force and displacements are related, right? So actually these are u now, okay? This tells you how the force and displacements are related. F equals KU, KO, KD, right? Displacement. So if you know this matrix, if you want to find these two, so we have already found the K matrix, but for each element. But we are solving it globally. So we have to define the global matrix. So this is how we define it, right? So this is K1. So I'll write this 10 to the power 6. So you should have like this, right? You remember this is for any element, this is its u1. So the first element, so this is u1 actually, and u2, right? This is u2 and u3, because this element is connected to u2 and u3. The direction is important, right? Where our first coordinate is, right? Our first coordinate is this, and our first coordinate u1, u2, and u1, u2, u2, u3, u2, u3. This is connected to u2 and u3. This is connected to u1 and u2, right? And I can write like this. Right. So the second element I can write K2, not K squared, okay? It's K2. So that's going to be 10. So this element is connected to its first node is U2, second node is U3, first node is U2, and second node is U3, right? This is just like the matrix notation, right? So our global K should be consist of 3 displacement, right? 3 nodes. So that means 3 by 3 matrix. So that means this is U1, U2, U3. This is U1, U2, and U3, right? So your first case is make everything 0 first for your convenience. You have 9 elements, right? Then consider each location. So this will cause you U1. So this element is U1 row, U1 column. Here no U1, okay? No U1, okay? But here, sorry, this is here no U1 was there, right? But here you have U1 row and U1 column. That means this is your, so when it meets here, right? Column U1 row, right? So that becomes 14, right? Becomes 14. Okay. So this is U1, U2. There's no such thing in here. U2, U3. It's there. U1, U2, right? U1 row, U1, U2 column. U1 row, U2 column. It's only this element, right? So this is becoming, this is how to assemble that, okay? So when you know the concepts, this is very easy, right? But this complex, but easy, right? So this element, U1, U3, U1, U3. U1 and U3 are not in same matrix, so there's no such element, so that is 0. And here also U1, U3, there's no such element, that is 0, right? And U2, U1, then you should be careful on that. I'll show you why. This is U2, U1, right? U2, U, no, not this element, in the middle element, I'll show you. U2, U1, only one element. So U2, U1. So that means it's here, right? Minus 14. And U2, U2. And that's the case. So you have U2 and U2 in this matrix as well as U2, U2 in this matrix as well. In such case, you just need to add those values, right? So 10 to the power 6 is out. It's there. So you have to add those. 10 plus 14 means it's 24. Then this is U2, U3. So U2, U3 means it's minus 10. Then there's no such other elements. This is U3, U3, only one element, it's 10, okay. This is U3, U2. U3, U2 means minus 10. So whatever happens, this is symmetric, right? So you can see this is symmetric. So, and then you need to determine your K matrix is OK, and you need to determine your F matrix and U matrix. This is for the element, right? So let's call this F1, F2, and U2, F3, and U3, right? U matrix is so you and me knows at first coordinate, first node, it's fixed, right? So it can't have a displacement. So that means U1 is 0. It's fixed, right? So U2, there will be some value, we don't know. Let's call this as U2 and U3, right? And for the force matrix, you have forces so you have external forces like this, right? So F1 is, so there will be a self weight of this portion, right? And altogether you have self weight of this portion. So I can write that self weight as W1 area volume into density times G, right? Mg. M is equal to density into volume. So that's in AL rho G, right? When you substitute that, because your A value is 700, so you can write W1 700 into L150. So you need to convert this 8,000 into 10 to the power 9 minus 9 into, I will take G as 10, okay, because I'm too lazy to get simplify 9.8. So this is 500 into the same thing, right? So this will give you around 8.4 newtons. Okay, this will give you around 6 newtons. And our assumption is this W1 is taken as equally here W1 over 2 and here W1 over 2. To each nodes we give you W2 because that's a only assumption, because we need to convert this self weight that is taken by these nodes, right? Because we are calculating at each nodes. So we need to give the representative self weight to each node, right? So simplest way is this part is taken by this node and this self weight is taken by this node. This part is taken by this node, right? Half of these into 3, half of these into 2. Half of top part is to 2 and half of this part into F1. And at F, you already have 1 kilonewton as well. So that means 1000 newtons, right? Okay. So that means you have, and here you have W2 over 2 and W. So the self weight is also acting downwards. And you have some another 10 newtons. So 1 kilonewton, right? So this will equal to W102 means 4.2, right? So this will equal to 4.2 plus 3. That's going to be 7.2 plus 1000. That's going to be 1007.2, right? So you have to add each. So what we did was the external forces exactly at that point. The other self weight are not acting at this point. So you need to make sure those are captured within these nodes, because we are solving the equation at these nodes, right? So that means the weight taken by that part is there, weight taken by that part is here. And this part is also count to 2. This part is also count to 2. So addition of these 3 will give you something around this, and W2O2 becomes 3 kilonewtons, 3 newtons, right? So you can write the F matrix as 4.2, 100 and 1007 and 2. This is 3. Now everything is done. Stiffness matrix is done. So you can write F is equal to K times U, whatever U or D, the displacement matrix, right? So this is going to be 4.2. Make sure the directions are all correct, okay? Our downward directions are positive, okay? Okay, so yeah, it's going to be how much? 3, right? And the matrix 10 to the power 6 over 15. This is going to be, you know, U1 is 0, U2 and U3. And if it is 0, we don't need to solve for that equation, right? It's nothing. So you can, this is U1, 2, 3, this is U1. So this is for the stiffness matrix. So you know, if U1 is 0, so you can close these rows U1 and close these columns, right? So you only need these two. This matrix equal to this. So that gives you 100, so 1000.7 is equal to 10 to the power 6 over 15. 24 U2 plus minus 10 U3. Okay. The other equation gives you 3 equals to what? 10 U3 minus 10, sorry, 10 U minus 10 U3 plus 10 U3. Right? So, sorry. When you add these two, so these 1 and 2, since the term here is similar, you can cancel this 10U3 and 10U3, sorry, 10U2. So that's going to be, sorry, this is 7 and 2, right? So I wrote it wrong. This is going to be 110. So U2 is going to be how much? How much is U2 going to be? It's going to be 0.005, around 0.005, right? And with this value, so that's going to be, sorry, this is 15, right? Zero 0.15. Q3 is going to be how much? That's also 0.015, right? From this equation you can obtain, right? So in that case, you can, so here I think we did a mistake. In this should be 0.2, and this is not actually 4.2 because this is body force is correct. Okay, this is body force is correct, but this is at the first node, right? So half of is here, right? Half of is actually here, but this is restraint, right? That's a reaction totally, right? So I'll get the total reaction is P, okay? So this is not actually needed, but this will not be represented in the answer. I'll show you why, right? So our assumption takes, our weight is taken by this half is taken by this node, right? So that's already included in that portion, right? And this next half and the next half is taken by this node, and the rest of it that is taken by this node, right? Okay, so what happens is actually this becomes P. We don't know this force because there's a restraint and there's a force P that we need to find, right? So let's call this P, right? So if your U1 is 0, the first thing you need to do is make your cross your first column and first row. If your U1 is 0, if your U3 is 0, third column and third column and third row, you have to cut it. Okay, that's how you need to modify your equation, and this will become, I think this is wrong. This is going to be 1. This should be divided by 14. So that's going to be 0.08, right? And this is also, I think, same, right? Exactly, not exactly equal, but yeah. Exactly equal, but this is like this, right? So with that, you need to find P, right? So we'll use Excel, right? So if you want, you can just take this equation because now you can take this row and this row because you know U2 and U3, right? You can find from this, or else you can write taking first row is equal to 10 to the power 6 over 15, 14 0, 14 U2 plus 0 into U3. So that's going to be 10 to the power 6 over 14, 15. So this is 0. This is minus 14. Okay, remember minus 14 into U2 and minus 6, okay, 0. This is multiplication. Okay, this plus this into this into this, right? So it's going to be 0 and U2 is 0.00108. And with that, your p-value will be recorded as 0. Sorry, 10.2, right? This is P. Is it a reaction? Let me check you. Okay, so one good thing is you need to go to the equation and you have the forces. You took the F1, right? F1. F1 is, this is should be negative, right? Negative. So this is negative 10 Newton. Is this a reaction? No, right? Just if somebody needs, they can take this as the reaction, but think about the actual what's happening. So there is a reaction. So think about this, just forget about this. There's a reaction of R, right? There's a reaction of R and there's a body force of W1 over 2, right? So that means F1 is equal to W1 over 2 minus R, right? So considering these two, you write this one. If you didn't have any load, body force, your total force is equal to R1, right? If you didn't have any load in that node, right? But you have some load here now, right? So it's not the direct reaction, right? So F1 is good. So your R is going to be, right? R is going to be W1. So we will write in characteristics. No, that's okay. So W1 over 2 minus F1, right? So I took the R in upper direction, okay? So that's going to be, this is 4.2, right? 4.2, and this is minus into minus, this is going to be plus, right? So that's going to be 1 4 Newton, right? So this is your reaction in upward direction, okay? So this should be the answer because you have these fundamentals, right? You have 1000 Newton and you remember lower half force 6 Newtons and the upper half force 8.4 Newtons, right? So altogether this reaction, what it should do, it should balance these forces, right? So R is equal to, this is simple statics. 8.4 plus 1000 plus 6, right? So that's going to be 4. So you need to be careful what you are doing, right? So in this F P force, it's not the reaction, it's the total force at node 1, right? But there's actually the reaction as well as some external load. But if you didn't have any external load, if W1 over 2 is 0, that means you don't have any external loads on that node 1. So what you are finding is directly will be the reaction, right? So that's why it became negative, because the force should be in upward direction. That's why, right? It's the total force, right? That's why it becomes negative, because that reaction should be in negative direction. So F1 is equal to R, right? And yes, then, okay, right. It's clear, right? So thank you very much.